Okay, this is homework 1, part C, part 1. So for this one, we need to derive the basic equation of statics for a fluid of constant density and constant acceleration. So let's say we did an experiment where if we had some water and we took the pressure at different heights of water, if we plotted this out, we would get a graph. So say this is pressure and this is height. We would get a graph that looks something like this, right? So what we want to do now is we want to find units. So we know that the pressure is related to rho and the gravitational constant g. So we get pressure over rho g h. And we want to set this as something that is dimensionless, like pi. So if we do this, we can see that pressure we can put into terms of kilograms over meters squared times meters per seconds squared. And this half the kilograms of the meters and the kilograms times meters per second squared, that's just a Newton. So then on the bottom, we get kilograms over meters cubed times meters per seconds squared times meters. And so when we do this, we can see that all of these cancel out, meaning that rho GH is dimensionless. So, or P over rho GH. The whole thing is dimensionless. And so from that, we know that P over rho GH is equal to 1. Okay, now to take this one step further, I've drawn a cube that we're going to use. And so first we need to label it. So in this cube, we have our area. There's just going to be the area of one side of the cube. And we have the height, which is the height from the water to the top of the cube. That'll be h. And we also need the height of the cube itself. And that will be dh. And we have two pressures that I'm going to be focusing on. One at the top, there's going to be ph. And then one at the bottom, ph plus dh. And so we know that the cube is not moving, so that the sum of the forces must be equal to 0. And those forces are area times ph plus dh, and then plus area times ph. And this is going to be negative because the arrow is pointing down. It's going the opposite way that we're calling positive. So that's why that's negative. And then also the mass, which is going to be pressure times volume, but the volume is just A times dH. And then also the gravitational constant G. This is all equal to 0. Oh, this is also negative because this force would be going down as well. This is all equal to 0. And then so when we evaluate that, we get negative dp over dh equals rho g. Or we can write it as dp over dh equals negative rho g. and that is the basic statics equation. Okay, so this is homework 1, part C, part 2. And for this one, we need to use the differential equation from C1 to derive an expression for the force necessary to hold back a wall of a rectangular pool of length W or length L with W with a fluid depth of D. So I've already drawn this, and we know is that the length of the pool actually does not matter, no matter how long it is. All that matters is the depth of the water and the width of the pool. So I've kind of just disregard the length here. And so what we want to do is we have the depth D and the width W. And what I'm going to do is I'm going to set Y equal to 0 at the top, meaning that going down is positive. What we also need to do is we need to kind of slice up this depth of water into sections. And these would all be equal. And I'm going to call one of those is called dy. Okay, so we're trying to find the force. The force is equal to the integral of df. And so what is df? df is just pressure times dA. Well, we can break those down even more. So integral of, let's redo that one. Worse. Okay. So pressure is equal to, it's equal to rho g h, or in this case y. I'm just going to call it y. And then A is equal to the width of the pool, and then we're going to do one of these dy. So one of these little square or rectangles we cut out. So that's equal to the width times dy. Okay, so now we can keep going and start putting on limits of this integral. But first we can take out rho g and w width. So now we're just evaluating y dy. And obviously for this one, we're trying to do all of the area that has water. So that would be from 0 to D, whatever that is. So now we can do this is equal to rho G W. And those are all constants. That's why they're not in the integral. And then that'll be y squared over 2, evaluated from D to 0. And then once we evaluate that, we can get our final answer, which is force. The force to hold back the wall would be equal to rho G W times D squared all over 2. Let's redo that too. Over 2. And that is the force required to make sure it stays